Our next speaker is Mr. Joseph Cassady. He is the Executive Director of Space Programs in the Washington, D.C. operations for Aerojet Rocketdyne, where he helps oversee strategy development and architectures for future space and launch systems. He obtained his BS and MS degrees in aeronautics and astronautics from Purdue University, as well as a graduate certificate in systems engineering from the George Washington University. Mr. Cassady led flight projects teams for the SX Artjet system, which still holds the record as the highest power electric propulsion system flown, and the EO-1 pulsed plasma thruster system, and has served on a number of advisory groups for NASA and the DoD. He is a corresponding member of the International Academy of Astronautics, an associate fellow of the AIAA, and serves as vice president of the Electric Rocket Propulsion Society, and as Executive Vice President of Explore Mars, a nonprofit dedicated to promoting STEM and human Mars exploration. Please welcome him for the delivery of a near-term interstellar mission enabled by the Space Launch System.
Thank you, and thanks very much for having us at the conference. I wanted to just thank the organizers. It's really exciting. I'm putting in a plug right now for the tour tomorrow. My wife and I went today because we're flying tomorrow. Go see the Infinite Space Explorers. It's amazing, almost life-changing. But yeah, I'm gonna take you on a journey now, something a little different. Been really excited to hear all of the plans and exciting things that are in the future. I want to talk about something that we can do today. Every piece of what I'm going to show you today is here and now. All we have to do is put those pieces together and we can go. So that's why we have been tasked over, a team has been working this for over a dozen years now, looking at the capabilities that exist. And I'll talk about some of the basis for that. So without and I want to thank my co-author, John Schumacher, who happens to be my boss, and couldn't stay. So what is the Interstellar Probe mission? Give you a little bit of overview. As I say, for about the last 15 or so years, there's been a team looking at this. NASA has actually chartered some of this work. It's focused on the notion of getting science return more quickly. And by that, I mean, as most of you know, we have 5 spacecraft that have gone on their way out of the solar system, the Pioneers, the Voyagers, and then more recently, New Horizons. And you heard Alan Stern give a really nice summary of the New Horizons mission. The one thing about all of those missions that's different than this is none of those were explicitly designed to be interstellar missions. And this mission is being designed for that purpose as its primary mission, to go beyond the solar system. And we're focused on getting to the local interstellar medium within 50 years. That sets up a very different set of optimization, and I'll talk a little bit about that in the talk. It has a number of key science objectives, and here I'm going to rely on my notes. Being the engineer, as we heard the other day in the science fiction panel, and not the scientist. I want to make sure I get these right. The big thing is we know a little bit now because of these other missions about the heliosphere. We've gotten a glimpse of what we live in. And it is this big bubble that is our neighborhood, and it's our habitable neighborhood. We tend to think of Earth as our cocoon, that we live in. And in fact, that's true. But beyond that, we have the heliosphere, the whole plasma environment and field environment around our sun. And we're traveling through the galaxy. So that's not a symmetric environment. And we've gone out in one direction. We've gone out in a couple of directions. We're getting different results as we go. And we want to understand more about that. So we want to gain that understanding. There's also the possibility, and we saw a really great talk the other day too about exoplanets. And so as our telescopes have revealed to us that there are numbers and numbers and numbers of solar systems out there, and we're seeing, protoplanetary disks around other stars and things like that, we can learn a lot by looking back at our solar system from outside. So that's another key science objective. And we'd like to understand how the sun and the galaxy affect the dynamics of that heliosphere. What's the nature of that local interstellar medium? And what are the origin and evolution of these planetary systems? So one of the ways we can do that is by going to the Kuiper Belt and studying those KBOs that we know are out there now. So that is, I think, a good summary. And then I almost forgot. As I said, we can look back at our circumsolar debris disk, observe it from outside, compare that to the telescope results we're seeing with these other protoplanetary disks around other stars. And then the last thing is the infrared sky. We live in a dusty environment, just as we have to observe through our atmosphere, and that prevents us from doing a lot. If we can get up to like Hubble and now Webb, we can do a lot more from in space. If we can go to the far side of the moon, we can do radio astronomy maybe better. If we can go outside of this local interstellar medium and get outside of the zodiacal dust and the environment that we live in, we can do better infrared measurements from out there. So all of these form the nucleus of the mission's science objectives. And then finally, this team has surveyed every kind of launch vehicle and mission option that we could look at to get there quickly. And I'll talk a little bit about that and how we settled on the combination that we got. But basically, it comes down to a really high C3 value, which means lots of throw weight. And if you remember what Alan Stern said about New Horizons, basically the biggest rocket you can get, he got that nice, super souped up model of the Atlas V with all those solids on it. We're going one better because we got a better rocket now. And we're keeping the spacecraft about the same size. So it's a combination of having the ability to take a lot of mass to a high C3. And I'll talk a little bit more about that in the talk and how we settled on the SLS. So the mission, what's it look like? We have a really interesting kind of overview here. You can see, first of all, I'll just say, and you can see this in the paper, the goal of the team was to get to 10 AU per year. Remember our little credit card the other night with the AU being the distance between the sun and the earth. So we're trying to get to 10 of those a year, which is pretty darn quick. I can't remember off the top of my head. I think it was around 3 or 4 for New Horizons, somewhere in that range, in the single digits. We were shooting for getting up to the double digit AU per year. And so that would allow us to get to 40 AU in 4 years. So that puts us out all the way to the outer solar system in 4 years. I think we go by Jupiter in 7 months. And we do a flyby at Jupiter. That was the one flyby we allowed ourselves. No interplanet flybys, no Venus Earth gravity assists or anything like that. It takes too much time. The goal here is speed. So we get out the outer solar system. There's a potential phase at the outer solar system because we're going to be going from 40 to 70 AU. At that point, we're going to be going through those interesting objects, those protoplanets out on the edge of the solar system. It's a little bit complicated because most of the instruments that we're using, the particle instrument measurements and things like that, the field instrument measurements, prefer a spinning spacecraft. And if you remember, Voyager had a spin platform and a despun platform. We could do that, maybe, but that's a little bit more complicated spacecraft. We can also despin the spacecraft and do this phase with a 3-axis stabilized spacecraft. And that would allow us to do the imaging of these Kuiper Belt objects. And then we go into the outer heliospheric phase, which is, again, going back to spinning. That's between about 70 AU and 200 AU. And that's over the next 10 years. So we go from about 7-8 years out to 20 years. And then finally, we get all the way out to 500 AU in 50 years. So that's our goal. And that's out in the true near interstellar medium. So the probe design is really, again, based on New Horizons. We've got an existence proof. We can do this mission. We can do the instruments. We know what those instruments were on New Horizons. And we could do it with the mass and the spacecraft mass and payload mass that are reasonable for this. So we set ourselves some goals there of about 60 kilograms for payload. Those are the instruments, and about a 478.3 kilogram spacecraft mass, which just so happens to be the same as New Horizons. That allows us also to use proven systems on the spacecraft, radioisotope thermal generators that we have and are producing more of now, communication systems that have been proven to work, the very large dish that you see for communicating back to Earth, and propulsion, the propulsion that steers the spacecraft, and if we needed to, can do the 3-axis stabilized environment. And then the meaningful science instrumentation. Again, most of these instruments aren't going to be new developments or anything like that. We know how to do the imaging. The one challenge, and I came across this as I was doing my notes for the science, is that when we get to the Kuiper Belt, we are actually going at 45 kilometers per second as we go by those for the flybys of potential Kuiper Belt objects. And it does require a little bit of improvement in the chip technology for those imagers, because otherwise you're going to get a blurry image as you go flying by. But then the optical and IR spectral imaging is also proven technology. So that's the concept. That's the spacecraft design. And so what we need now is we need the ability to get us going really fast. So how do we do that? And I think this is my video.
The moon will be different than the last time. We plan to explore more of the lunar surface and learn how to live. The space launch system is now counting down to liftoff of Orion on its maiden voyage to the moon. And here we go. Hydrogen burn-off igniters initiate. 7, 6, 5. 4-stage engine start. 3, 2, 1. Boosters in ignition. And liftoff of Artemis 1. We rise together back to the moon and beyond.
We are all part of something incredibly special, the first launch of Artemis.
This view of Earth from a human-rated spacecraft not seen since 1972 during the final Apollo missions.
Distant retrograde orbit. We're going to be about 38,000 miles away from the lunar surface. We're going beyond anywhere we ever went for Apollo.
The Orion spacecraft is barreling its way back home after circumnavigating the moon and beyond in an elliptical distant retrograde orbit. Splashdown. Orion back on Earth.
So that was Artemis 1 last November, and that changes everything because now we've got the rocket. We don't have to, it's not a paper rocket anymore. It's not a PowerPoint. That flight was as close to flawless as we could have expected. I can tell you some stats if you want, but we're down in the very small percentage of deviation from all the expected values, and we got an A+ from our NASA project folks. So we're confident we've got a rocket. How we evolved that rocket and why it's so important is because we really don't have the time, as I said, to go do those flybys to gain velocity in the inner solar system. So we've got to be able to combine enough throw weight with that C3 and enough volume in that and mass capability on top of that rocket. So right now we're launching Orion to the, we're going to do that with Artemis 2. We have a Canadian astronaut on the crew for Artemis 2, Jeremy Hansen. Orion's a pretty heavy vehicle. And obviously with crew, we just heard people take a lot of consumables and things, but we can also remove that put a cargo fairing on, and we can launch really big things like bigger telescopes. And we can also launch stages on top of it. So that's what I'm going to show you today. We went through a whole lot of gyrations and looking at, what are the things that we could carry on top. Remember, our spacecraft's tiny. The spacecraft's like a speck inside this big fairing. We're going to put extra rocket stages on top of the SLS, and SLS will get us going straight away past low Earth orbit, past the moon, right on out into the solar system, and then we'll fire up those other stages to get us going even faster to get up to that, hopefully, close to 10 AU. So we've done all those trade studies. One of the points that I make in here is it's really important that we do it this way because we're going to have radioisotope generators on there. We can't hang around in low Earth orbit with nuclear systems. Nobody wants everybody wants nuclear systems to explore the solar system, but nobody wants them close to Earth, right? That's where they're dangerous if anything would go wrong and they come back. So this won't stop. It won't stop for gas. It's going to go straight on out. And that's important to meet the requirements for these nuclear regulations. And since we've now demonstrated that we can do this with Artemis 1, we're confident that we could support an early 2030s launch. And this is just a chart that talks a little bit about the evolvability of the SLS system. So all the key elements are there. On Artemis 4, the first 3 flights with the crew are just going to take Orion and 4 crew out. And then beyond that, we're going to start taking more and more payload capability. So we've developed a better upper stage, and that's the one evolution we're going to do with Artemis 4, and that's in about the 2026, 27 timeframe. And then beyond that, we have one more evolution, and that's better solid rocket boosters. We have now steel case solid rocket boosters that go back to the shuttle. We're going to evolve those to a composite case solid and get a little more performance out of those. We're upgrading our RS-25s at Aerojet Rocketdyne. We've got those up to tested now at 111%. If you remember the shuttle days, when we would go at throttle up, we'd go to 104%. We're now at 111%, and we've even pushed them beyond that on the test stand down at Stennis to 113%. So maxing out on thrust, we'll get up close to 9 million pounds of thrust, and we can take payloads of 50 metric tons or greater out into the deep space environment. So what are we going to do with that payload and volume that I talked about? How do we use that? And as we did this trade study, we first said, and this was again 15 years ago, so SLS was at that point still a paper rocket. We said, what could we do? What rockets are out there that we could use? And keep in mind, we need C3s of up close to 200 is what we're really shooting for. So the C3 on the bottom of the graph here, you can see ranges from about 0 to 120 here. And you can see in the red line there, that's a standard type of Falcon Heavy that, a lot of folks are familiar with now where you're recovering it. If you look at the really light blue line or teal colored line, that's a fully expendable Falcon Heavy. And note that big difference there. Reusability isn't free. You pay a steep price in performance for reusability, especially if you're trying to do what I said, go to the outer planets. And so if we assumed even the best, and then we also had a Delta IV Heavy and an Atlas Heavy. That's, by the way, that green one is what Alan used on New Horizon. The best we could do with a payload mass that was of interest is about 100. And that's just too limiting. Oops, I did something. Oh. So we started looking at now with SLS, okay, let's take that SLS launch, and now let's start putting other stages on top. We have a Centaur stage that we've used for years on top of Deltas and Atlases. So we stacked the Centaur on top of our EUS. And then we said, that's getting there, but it's not quite there yet. So we had a Star 48. We've used that for the Parker Solar Probe. Some of you are familiar with the Parker Solar Probe. So we took the Star 48, we put it on top of the Centaur. We did a lot of different trades. Everything had to be something that was available and had flown before. We weren't going to look at some new, fluorine type stage. So we put those together, we ran these curves, and you can see the best we got in that. Oh, and the 500 is that's our spacecraft and payload. We're shooting for that as our target, that black line going across. So you can see with the Centaur and the Star 48 BV stacked on top of the SLS, we're getting out beyond just a little past 400 for our C3 values. So definitely in the right ballpark, confident we can do it. We've got the rocket to do it. So all we need now, as somebody said the other day, is the go ahead and the funding, and we can start building this mission. So I think what I wanted to leave you with in summary is we've got the concept, we've got the spacecraft design. A lot of scientists have collaborated on this. Still, final decisions need to be made. There's a lot of interesting things we could do. One of the things that this allows us to do is pick the launch date, pick where Jupiter is, and decide which direction do we want to leave. And that's really enabling and fun too, because we can say, do we want to go out the nose of the heliosphere? Do we want to go out the tail? Do we want to go out of plane? If we go out of plane to someplace like Quayar, do I say that right? the interesting Kuiper Belt object, it's a little bit out of the ecliptic. We're going to lose some velocity, but that's a choice. We can trade that off. Maybe we take 60 years to get out there to the 500 AU instead of 50, but we see something else interesting along the way. So the scientists want to do that. And I didn't mention, but in my last chart, we did max out without doing a powered Jupiter flyby at about 7 AU per year. We think if we do a powered flyby, and that's a question of what stage would we use to do that, probably the solid. Can we keep the solid for that long before we fire it in space, in vacuum? Are people comfortable with that? That we could get up to about 9 AU per year with a powered flyby at Jupiter. And it gives us the ability, as you saw on the mission overview chart, to reach some incredible places in short amounts of time. Still 50 years. You still have the problem of, a young postdoc is starting their career in their late 20s. They're going to be in their 70s by the time we get to 500 AU. But we've even had people looking at, and I was really intrigued by the last talk, we've had people on this team looking at the generational handoff and how to, set the mission up so that we can basically bring along the next generation. And Voyager's a pretty good example of that if you think about it, because there were a number of folks who were involved at the very beginning in the 70s who handed it off to other folks. And over time, that mission continued, because originally Voyager wasn't intended to go for as long as it has. This one, we intend to go for 50 years. And we believe with this spacecraft technology, we could probably go for 100. So I will stop there and take any questions.
Thank you. Great talk. This may violate some of the rules you had for the mission concept, but would radioisotope electric propulsion give you a little bit of additional terminal velocity, or would you view that as too much risk and not enough benefit?
No, it's a great question. And we did look at a lot of REP prior to this really getting going as other alternatives. And there have been other kinds of missions like the T8, 1,000 astronomical unit, I think that Bob Frisbee and those guys did. I think that might be an enhancement that we could look at. I think the problem is, and it really gets down to my comment back earlier about the spin, despin, whether we have a spin platform or not. We tried to keep the spacecraft really super simple and keep that mass really low. And that kind of goes against that. But it's a great thought. Maybe on Interstellar Probe 2.
So riffing...
Oh, there you are.
Great talk. Riffing off the previous question, how much of the RTG stockpile will this thing eat? And I only saw 2 on there, but I would assume for that long of a mission, you might want to have more than 2.
Thank you very much. So actually, it's a couple of things. One is, right now, happens that we build the MMRTGs. So we're doing the MMRTG. Well, we did the 2 that are on Curiosity and Perseverance. We're doing the ones for Dragonfly. Efficiency of conversion is not the best, but they're very robust and resilient, multi-mission because they can operate in atmosphere or in deep space. But we're also working on the next-gen RTGs for NASA. And one of the things, and then there's another program called the dynamic RTG, or dynamic radioisotope DRPS, dynamic radioisotope power system, which uses Stirling converters. So a number of ways that we can get away with using less plutonium because we're increasing the efficiency of the conversion. So that I think is going to play into this, because you're absolutely right. You know, we have to be good stewards of the limited stockpile that we do have.
Did you also look at the upcoming spaceship from SpaceX?
Starship,
excuse me. Yeah. Starship.
Yes. There was some consideration of Starship, but again, you know, we sort of limited ourselves to concepts that could go direct, and Starship unfortunately has to refuel in low Earth orbit. So you have a long dwell time to get that refueling done with a payload that has a hot plutonium power source. Not a concept that I think gets past the NPR.
Okay, and just following, what is your time scale here?
We're looking at launching in the early 2030s. So, I mean, that launch date would depend on several things. Number one, funding, getting picked as a mission, getting funding. And then the second is really determining, you know, what's the date that we want to go, and that's going to set where we go. And there are some 12-year cycles there, you know, with Jupiter. So you have to sort of think that all through early on.
If you're concerned about long dwell times for these radioisotopes near the Earth, have you considered parking orbits around the moon?
You could, but you know, again, the goal is achieve a high flyout velocity, and unless you're going to do some kind of Oberth maneuver, we did look at, I didn't mention that, but we did look at an Oberth type thing, diving into the sun, again, based on Parker. A lot of it was based on Parker. Part of the problem with that is then you got to shield the spacecraft, and you end up, you know, it's one of those, somebody said it earlier, you know, there's no free lunch in engineering. You do one thing and you gain this, but you end up losing because you got to add a lot of mass just to keep your spacecraft from getting too hot when you get in close to the sun. But the parking orbit around them, I think our goal is direct departure straight to Jupiter. Yeah.
Okay. For a very fast mission like this, is there any prospect of a flyby of more than one Kuiper Belt object, or is it pretty much one and then you're gone?
Yeah, it's a great question too. In the science report, and I recommend in the paper, I did put all the references in there. There's a super summary of the whole project, science, and all that, and that APL put out. The problem we have right now is we just don't know. The you know, locations and the positions are not well enough known to say, yes, we would like to go C2. We think maybe picking one and, you know, setting that as a goal is good, but you'd hate to promise that you could get to, because we just don't know how everything's going to line up out there. And again, we're moving really fast when we get out there. So doing any kind of, like New Horizons did a maneuver to get to the KBO they went to and burned a lot of propellant to do that. And we just think that would probably kind of get back to Sonny's question about REP and things like that. All of those things would add more mass to the spacecraft and kind of, you know, go against our primary directive, which is small, simple spacecraft, big rocket.
Well, thank you very much.
Thank you.